the evolution of the stresses as I go through the thickness of the beam. Okay? So this is going to be sigma max, got compressive. The bottom is going to be sigma max tensile. And if the cross section were a rectangle of dimensions that we had seen before, then sigma max is E times epsilon max. Now if I drew it in 3 dimensions, here is what it will look like. Okay, so all I'm doing is I'm taking this beam and twisting it and showing you the view. Okay? I'm going to draw the centroid. And I'm going to draw a line that is going to divide the cross section into 2 halves. This is now the cross section of the beam being shown to you. And as I have showed there, the stresses on the topmost fiber of the cross section are going to be compressive, but the largest value. They're going to be arrows of the same magnitude. Okay, so I can draw them by a straight line here. These stresses will reduce in intensity linearly as I come to the center. At any point here. You can see that the intensity reduces. So this was point C. This was B. Does this make sense to everybody? This was point C. That's the point C here. That's a point B. That's a point B there, which means that the stresses on the bottom portion, they're going to start increasing from a 0 value at the center line all the way to a maximum value at the bottom. And I'm running out of space here. Does this picture make sense to everyone? What am I doing? First question is, does this figure make sense to everybody? Yes, sir.
In the first block, what does the arrows in the opposite direction represent?
Which one? This one?
Yeah.
That's a stress. That's within the sigma max. Right? These are also sigmas. But that's going to be in compression. Okay, all of these arrows at the bottom and the top are of the same magnitude. This is in tension, which means that if I choose any point on the cross section above or below this line that I have drawn, the stress at the point will be either tensile or compressive. So if I choose a point here, what's the stress going to be here? Tensile. If I choose a point above, the stress will be compressive. Okay? And so this is the evolution of the bending stresses as I go from the center line. And the center line is now going to have a special name. Okay? It's going to be called as the neutral axis. So this line here is going to be called as the neutral axis, and I'm going to define that in a minute. My shorthand notation for the neutral axis is NA, and it is also called as the bending axis. And if you note carefully, it is also a axis of symmetry, which means it's a centroidal axis. So now you see the connection between what you're doing in statics. You are asked to find centroids of odd shapes, like an L shape, a T shape, whatever shape that they asked you to do. We need to know the centroidal axis or the neutral axis, because if you have a bending stress applied on the body, what is the stress at any point on the neutral axis? 0. The bending stress at any point on the neutral axis is going to be 0. Okay? And that brings us to what I wanted to do today. First of all, I'll define the neutral axis. By drawing the following figure. Okay, so once again, pardon me for drawing many figures. You don't need to keep drawing all of them. You can just take one figure and then keep writing on top of it. Okay? So here is a figure. Okay, so this is just a view of the beam in 3 dimensions. This is the length scale. This is the x-axis along the length of the beam. Okay? We discovered that there is this line, the neutral fiber, which is along the length of the beam where there are no stresses on that neutral fiber. I can have a collection of neutral fibers if I slice through the beam. If I slice through the beam, I can have a collection of neutral fibers in the following manner. So any line drawn on that plane that you're seeing is going to be a neutral fiber. Okay? So any line here, any line there is going to be a neutral fiber, which means that it is not going to have any bending stresses if there are bending moments acting on the body. This is a neutral fiber. As are these, etc. Does this figure make sense to everybody? If I shade it out. So there is this plane along the length of the beam where I have a collection of lines, horizontal lines, where there are no strains or stresses if there is a bending moment acting. This collection of neutral fibers lies on what is called as a neutral plane. Okay, so this shaded plane that I've drawn is called the neutral plane. The intersection of the cross-sectional plane and the neutral plane denotes the neutral axis. So this line here, which is the cross-section plane intersecting with the neutral plane, is the neutral axis. This is the intersection of the neutral plane and the cross section. We will take it for granted, without any derivations, that the neutral axis is the same as the centroidal axis of the cross section. So no derivations. Neutral axis and so at any point on a centroidal axis, or the neutral axis, the value of the bending stress is 0. If at all you remember anything from bending stresses, I want you to remember this one particular line. Okay? Somebody will come go to an interview, show you the axis of symmetry, which is essentially your centroidal axis, calculate the bending stress at any point on the centroidal axis. What do? No calculations, 0. Why is it 0? Because of just what we described here. Alright, I want to stop and see if there are any questions. There's one more thing I need to do and then we should be good for bending stresses. Is everybody on the same page? You're seeing this visually as to what's happening. I have this beam here, length of the beam, not showing you the whole beam, but you can imagine slicing this beam by a plane, passing through the center of the beam. That plane is a collection of horizontal lines. None of those lines have any bending stresses. And that plane is called the neutral plane. The intersection of the neutral plane, which is a plane slicing through the beam, and the cross section, which is the plane that you're seeing here, that gives you the neutral axis. No derivation. There is a derivation, but I'll skip that for the time being. The neutral axis is the same as the centroidal axis. Okay, so now we come to what I wanted to do today. The last thing for the day. As we always do, I want to relate the bending stress to the bending moment and the geometry. The bending moment. And the geometry of the beam. It's a fairly simple and straightforward illustration of this derivation. Okay? I'm going to look at the beam, look at it from a three-dimensional point of view. Okay, so this is the length of the beam. Okay, so this is the x-axis. The axis of the cross-section that you see is the y-axis and the z-axis. Centroid. This is the z-axis. Here is the centroid. And I'm looking at a bending moment acting on the beam, okay, along the following sense. And for context, I'm going to draw the two-dimensional picture. Everybody good with this? Here is the context. Beam. X-axis, y-axis, z-axis. I have a bending moment acting in the following sense. If I draw that bending moment here, what would be the direction of the bending moment? So here is the beam in 2 dimensions. This is the 2D view. I'm slicing through this cross section here. Okay, so that's what you're seeing here. If I were to draw the bending moment on this cross-sectional slice, which you will be doing for multiple problems from now on, what is the direction of that moment m?
To the page? Like along the z-axis into the page like that?
Along the z-axis, is it negative z or positive z?
Positive.
Watch this. Z-axis is the axis coming out of the page. Right hand, not my left hand, right hand. Curl of my fingers is the sense of the moment. The direction of the moment is in the negative z direction. So if I have to draw this out on the figure here, it is going to be looking in the following manner. My arrow will be a little difficult to decipher, but the thing that is a saving grace is that this double arrow here, the double arrow denotes the direction of the moment. This can be confusing, okay, depending on how you look at it. There is no ambiguity on this at all. The double arrow is pointing in the direction of the bending moment. Okay, and this is directed along the negative z direction. So far so good, everybody? Okay. Now, what we are going to show is that because of static equilibrium, all the stresses that are caused by this bending moment on the cross section that I am seeing, they have to statically balance the moment that is applied. Right? I have a body, I am applying a bending moment that causes stress. The stresses caused by the bending moment, if I take up the totality of their effects, they have to be the same as the bending moment applied. Right? The cause and the effect have to be equal to each other, otherwise it's not in static equilibrium. So, I'm going to choose a point at a distance y from the neutral axis. So the neutral axis is this line here. And I'm going to look at the direction of the bending stress. Can somebody tell me what is the nature of the bending stress at that particular point, at this point here? Is it tensile or compressive? So imagine it this way, okay? So I don't want to break this computer keyboard, but so here is the cross section. Okay? My hand is the neutral axis. If I look at the way the bending moment is applied, the bending moment is trying to push the top of the keyboard into the page and pull the bottom of the keyboard out of the page. Does this make sense to everybody? So which means all the points above the center line, they are going to be in a state of? Once again, here is my thing. But this is probably an even easier example. I am applying a bending moment. This is the center line. The fibers on the top are getting pushed, the fibers on the bottom are getting pulled, which means that the top fibers are getting squeezed, so they are in a state of compression. And the fibers on the bottom are in a state of tension. Okay, so that's the way to visualize this. So if I look at the stress there, that's the arrow that is pointing into the page. Okay, so I'm going to call that as sigma. And that sigma is acting on a small area dA. And here is the thing. I collect all of these sigmas acting over the entire cross section and I sum their effects up. I should be getting what? I should be getting the bending moment applied. Right? So first thing is I take the sigma, convert it into a force. Stress times area is force. I take that force, multiplied by the distance, I get the moment. If I keep doing this, if I don't have much of a life, and if I keep doing this for each and every point on the cross section, I should hope to get what? I should hope to get the total moment M. Does this make sense to everyone? Stress at a point. Point means a small area. Multiplied by the area, you get a force. I take that force, which is an elemental force, because there are millions of those forces at every point in the cross section, other than the neutral axis. I take those forces, I multiply them by the distance y, I get these small moments, I add up all of these moments, I should be getting the total moment m. We don't do additions, we do integrations. So here is the deal. So m is equal to the following. Integral over the entire area, sigma times dA multiplied by the distance y. Sigma times dA gives me a force. Y times the force gives me a moment. And if I take up this moment and add it all through the cross section, I should be getting the total moment that I see on the cross section. Does this make sense to everyone? with one small caveat. Negative sign. Why do I need the negative sign?
We're in compression.
Or I could be in tension. If I am in compression, then the direction of the bending moment, look at this, my fingers aligned with the arrow that I'm seeing here. If I am in compression, the direction of the bending moment due to the force caused by this is going to be along the negative z direction. If I am in tension, is the direction of the bending moment going to change? It should not change, which is why I have the negative sign there. Okay? And so with that, let me now do my substitutions. Last few minutes. Instead of sigma is minus E times y by rho, which was E times epsilon, so epsilon was minus y by rho, so I'm going to do that substitution here, so I get m as integral minus E y by rho times y times dA. Rho is a constant, Young's modulus is a constant, negative negative makes it positive, so that m is E by rho. This is an area integral, so it is double integral. We will not be evaluating it. Y square dA. What's this called? What's integral y square dA? What was integral r square dA from torsion? We call it as the polar moment of inertia, capital J. So in this case, this is going to be called as the area moment of inertia about the neutral axis. Okay, so this one here is called INA, which is the area moment of inertia. INA, area moment of inertia about the neutral axis. And I am looking for one more minute. I want to complete this so that we start doing some problems in the next class. So I'm just going to write m as E by rho times INA. But I'm not a fan of this E by rho creature because rho is a fictitious quantity, right? This radius of this large cylinder that I'm wrapping the beam around. So I do the following substitution. Sigma is minus E y by rho. So that E by rho is minus sigma by y. And if I now do the substitution back in there, m is minus sigma INA by y. I'm going to go ahead here. Sigma is minus m y by I times INA. M is the bending moment. When I consider the bending moment here, this m was applied in accordance with the sign convention. So here, which means if I look at the beam, this is it. If I flip the direction of m so that I am not in accordance with the sign convention, then the negative sign will go off because my moment is now negative. Okay? So I'm going to stop here. This is a lot of stuff to digest. I'm going to post like a detailed derivation of bending stresses. Please try to go take a look at it and we can converse. Thank you.
No, no point.
I'll do it soon. Yeah, sure, thank you. Yes, sir.